Okay, so let's go to the video lesson for building a custom inverse kinematics controller. And the goal is to have a model that will take us from a twist to independent module control. So here, a twist will give us the linear velocity of the robot in Vx, Vy terms, and the angular velocity of the robot, omega z, or rotation around the vertical axis. And we need to convert that to 6 independent model controllers. So we need an angle, and for the angle of the wheel, and we need the angular velocity, or the speed at which the wheel will rotate. We need 6 of them. Okay, so in order to do that, we need the position of every wheel. So we will have for wheel I, we have the xi and yy, the positions, yi, the positions. And then we're gonna calculate the velocity based on the twist. So we have all the components of the twist here, and the position of the wheel. And we're gonna use that information to calculate the wheel speed. So let's have a look at some code. So first thing to note is that we're going to declare here some parameters. This is ROS code, so I'm going to teach you a little bit of ROS right now. So we're going to declare some parameters, wheel radius, and the wheelbase, and track width. So the values are there, and you need to make sure that this corresponds to what's on the URDF or Zacro file. Right? Those numbers must match, or we will be in trouble. Okay. And then we're going to use those values to compute the positions of the wheels. Okay, so we have the X components for the wheels and the Y components of the wheels. So we have the X for the front wheel, which is wheelbase divided by 2. Then we have the X component for the middle wheel, 0, and the X component for the rear wheel is negative wheelbase divided by 2. And then we have the left wheel, the right wheel. Okay, so it's track divided by 2 and negative track divided by 2. And all of these values, again, need to correspond to values in the Zacro or URDF. So we have the same formulas, the same calculations here. They must match, or there will be problems when we try to control a robot. Okay, so with those values, then we can set a list of tuples, okay, which will be the wheel positions, right? So for each wheel, we define a tuple corresponding to their positions, x, y coordinates for each wheel. So for each wheel I, these are the xi, yi, the position of that wheel. All right. Then continue with the code. Here we have publishers, right? We're going to publish position controller commands, velocity controller commands. So we need 2 publishers, okay, ROS publishers, and they're float 64 multi-arrays. And then we have a subscriber for twist. Remember, we are going to receive a twist, and the typical name is command velocity in ROS. That's the typical topic name for a twist. And what is this twist? Well, this twist will give us the linear and angular velocities, or the Vx, Vy linear, and omega z angular, rotation around the vertical axis. Now notice that a twist will actually give us components in z axis, in all 3 axes, right? But we only care about a plane because we are a mobile robot, not a drone. We don't fly. Okay, so here's the subscriber for twist, and this subscriber has a callback, a command velocity callback. So every time we get a twist message, the callback will trigger, and we will do the actual computation here. So we get the twist message, and we extract the Vx, Vy, or the linear velocity component, and the omega z, or the angular velocity component. And again, there are more components there, but we are a mobile robot, so we don't care about the other components. And then, so that's the Vx, Vy, and the omega z in this formula. Okay. Then we are going to call a function called apply inverse kinematics with those 3 values as parameters. And this function should give us 2 arrays, an array of steering commands and drive commands, which we are going to publish. Right? We have publishers for this. So we're gonna, those publishers will publish float 64 multi-array values, and we just publish those two arrays. So this corresponds to, if we scroll down here a little bit, this corresponds to computing this set of steering commands and drive commands and then publishing them to those topics. Okay, so let's actually go to the meat of it, how to compute these things. So we are going to the apply inverse kinematics function. We receive the velocity component. And we start with empty list of commands. This variable pi over 2 just for simplicity later. And then for each wheel I, we obtain their positions, its position, sorry. For each wheel I, we obtain the position of the wheel. And then we're going to compute the velocity for that wheel. Okay, so to compute the velocity, we follow that formula. So is Vx minus Wz times Yi and so on and so forth. Just follow this formula. And then that gives us the velocity vector. Now we need to compute the angle at which the wheels, that particular wheel needs to rotate or steer to. And we use the components of that velocity vector. Okay, so given those two components of the velocity vector, the steering angle will be the arctangent 2 of the components of the vector. That gives us the angle at which the wheel should be moved or steered. And then we need to compute the angular rate at which the wheel should spin. So that will be the magnitude of the velocity vector divided by the radius of the wheels. Okay, so the drive speed or the magnitude of the vector is just the square root of the square of the components of the vector. And then the velocity, the angular velocity, is that drive speed divided by the wheel radius. And just some optimizations. We handle the case where we have zero velocity, but this part is important. Actually, our wheels can only rotate in the negative 90 or 90 degrees range. But angles given by the arctangent 2 might fall outside of this range, right? So we need to wrap around, like they say, or we need to convert those out of range angles to within range angles, so that we basically minimize the turns. We make the wheels not turn by too much, just turn by as little as possible. So it's an optimization. And once we have those angles and velocities, we just add them to the array, and we return the arrays. And that's essentially it. So we have the angles, we have the velocities, and now we can actually try this. So first, before we try this, I want to show you a little tool that we're going to use, a joystick that will make things easier to test. So this virtual joystick is pretty handy. So I already installed it, but you can follow these instructions to install it. So I'm just going to run it and show you the twists that are published. I think I need to source some workspace. And there you go. That's the joystick. So this joystick will publish twist commands to the command velocity topic. So I'm going to echo that topic to see some commands. And here is the topic, right? So it has a linear and angular velocities, and for each of them it has x, y, z components, one for each of the 3D directions, three-dimensional directions. But as I said, because we are not a drone, we don't fly, we just care about x, y, because we can move only on a plane. We are mobile based. And we can only rotate around the vertical axis, so we only care about rotation around z, because we don't pitch, roll, yaw. We're not a drone, we're not an airplane. Okay, but twist gives you all of these values, give you 6 values, right? So because it can also be used for drones or other kind of robots. But for our mobile base, we really just care about x, y for linear and z for angular. Okay. Now, let's try the joystick. So first of all, notice that there's a holonomic version mode that we're not using right now. So in non-holonomic, we only use X for linear and Z for angular. So notice how no matter how I move, there's only an X component for the linear velocity and the Z component for the angular velocity. Okay, so this is whole non-holonomic motion. But if I activate the holonomic mode, now the Y component of the linear velocity is available, and there's no real rotation here. So we just move. We can move like a little crab. You'll see later, but it changes how the robot behaves if I activate the holonomic mode. So I'm gonna deactivate it for now, and so let's actually run our simulation. So let's go to the workspace, and let's not forget to source it, obviously. And then we're gonna just build it just in case. I already built it before, but just in case, don't forget to build it. And then we are going to launch our simulation. So RCSHL1 gazebo, TP1, launch the pipe. And here everything is ready. If we look at the terminal, we see joystick broadcaster is ready. All the drivers, drive velocity and steer position controllers are ready. So let me just rearrange the windows a little bit so that we can see things in a more clear way. And then I'm gonna try move the robot, and nothing happens. Right? Nothing happens because although our controllers are listening, we don't have the drive mode activated. Right? We haven't activated the swerve drive controller. So we open another terminal, and we source the workspace, and then we run the swerve drive controller in the control package. And now you see the controller is initialized, wheel positions are this, and wheel radius is this, and we're ready to move our robot. And now the robot's moving, look at that. But we are in non-holonomic mode, so it's behaving just like a standard differential drive robot, or like an Ackerman steering robot. So we are sending, by using the joystick, we are sending only the X component for linear velocity and only the Z component for angular velocity. Okay, so see, if I go just on the straight to the left, it rotates in place. Right, look at the wheels, how they're spinning, rotates in place, and depending on how large my turns are, the wheels will have bigger or smaller steering angles. Okay, and there was no way we could have predicted those angles manually. That's why we need a controller, a special controller. Now let's activate the holonomic mode, and let me be careful here because I can crash my robot if I move too fast. So let's see what happens if I just go upwards. Well, we just go forward as normal. But look, if I try to go to the right, or to the left, sorry, then the road moves like a crab. There's no steering. There's only purely Y velocity, linear velocity in the Y side. So I can move like a crab. I can move a little bit like sideways. I'm not sure how to express this, but you can see it here. So it's very special motion, right? And this is only possible because we have this swerve drive or crab-like drive mode that this special SHL1 robot allows us to use. Now back to non-holonomic, it starts behaving again like a regular little car or differential robot. And that's it. We're done. We have successfully implemented this swerve crab drive inverse kinematics controller, and that's it. I hope you have enjoyed this process as much as I had. See you next time.